Thank you. It's a great pleasure to be here. Mathematics and physics have a beautiful long history, which goes over many millennia. Many different cultures and people have contributed to this interplay over the millennia, including the Greek mathematicians and philosophers. Thousands of years ago, they thought that mathematics should explain everything. They thought that there are 5 basic ingredients explaining everything, and these 5 basic ingredients are related to Platonic solids. Why Platonic solids? Because those were the most beautiful symmetric objects they could identify. Scientists and mathematicians continued from different places, different times. For example, Biruni measured the radius of the Earth with great accuracy using just simply geometry by going over the top of a mountain and looking at the horizon and seeing that the horizon is not 90 degrees relative to vertical. And just by measuring how much is that angle, he measured the radius of the Earth by knowing the height of the mountain and that angle. Now, we think we are very smart. We think that we have discovered a lot of things that were not known before. Well, that's partly true, but many things were also discovered a long time ago. For example, the height of the atmosphere. How many of you think the height of the atmosphere was known 100 years ago? Raise your hand. How many think it was known 500 years ago? Raise your hand. Why do you think it's 1,000 years ago? How could it be? How would they do it? Did they send a balloon up? Or maybe they went with a rocket up there? How could they know it? Simple. They just noticed this simple picture. They had already discovered that the Earth is round. Okay. And they said, well, when the sun goes down, the sky above us doesn't get dark immediately. Why? If there was nothing above us, it should have been dark immediately. But it's not. So what happens is that as the sun goes down, it can still reach the upper edges of the atmosphere, and it will brighten it up, and we are seeing that little light from there. And that's why the sky is not dark. But when the sun passes the last point which you can touch the sky above us, then the sky will be totally dark. Just this simple reasoning gave them an estimate of the height of the atmosphere. The value they got was not perfect, but still, it shows that simple reasoning, just thinking clearly, can guide us. And people did this 1,000 years ago. My area of research is string theory. Now, string theory is a very mathematical theory trying to unify everything. It's a very ambitious theory, trying to explain all the forces. It's trying to explain how the universe works at the smallest scale, all the way to the whole universe, including not only the galaxies and as far as we can see by eye or by telescope, by what means to validify how the universe works. So it's a very ambitious theory. But the basic postulate of this theory is that while we think that the fundamental entities of matter are particles, like electrons and the atoms made of protons and neutrons, but actually these objects which we think are like point-like, they're actually not point-like, but they're like little loops of energy. Strings, we call them. So you have a picture like this, where the individual quarks in the nucleus, like the things that constitute protons and neutrons, are actually themselves, if you zoom in and if you look through them, you find that they are not actually point-like, but loops of energy. And these loops of energy, these strings, can come together and join. Two strings come together and join, and that gives them a force between them. And they can also split. So this interaction, splitting and joining of strings, explains all the forces in nature. Electricity and magnetism, gravitational force, radioactive force, all of these can be described by this simple diagram. We call this the pair of pants diagram, because it looks like pairs of pants. So physicists have this funny attitude of trying to name things in a familiar way, and that is actually related to how we actually feel about mathematics. We have to think about it in terms of objects we can understand. Complex ideas are something that we have to bring it into a language and terms that are easy to understand. Physics have the reputation of being impenetrable by non-physicists because of its formidable mathematics. I would like to basically convey the idea that that is not really the case. Physicists, just like ordinary people, will not understand what's going on unless they can translate those complicated mathematics into tangible, simple things. So if anybody kind of gives you the impression that somehow physicists love complexity, that's at all not the case. We love simplicity, and if something is complicated, we try to cut it to simple things so that we understand, just like everybody else. So, dimension of space, according to string theory, is different from what you might think, that you think that there are 3 spatial directions and 1 time, but actually string theory says there are 6 more extra dimensions which are hard to see. They are hard to see because they're kind of so tiny and they're kind of difficult to measure in the experiments, and we cannot see it with our eye. It's kind of like this. You see, at each direction you can see a long direction, but then there are these tiny, tiny spheres, like these bubbles of these universe, that are hard to see, and we think that these spaces are 6-dimensional. We do not know how to actually see it yet because they're so tiny that our best accelerators, or if you want to call them the best microscopes that we have, cannot detect such a small distance. So this is a kind of an imagination of how they may look like. So here I have drawn on the blue as a sheet parts of our space, a 2-dimensional sheet, which is part of the 3-dimensional space we are at. And that red donut-shaped object is part of this extra dimension. Now, you can have objects in it. For example, a string could wrap around a circle inside this extra dimension, and from the perspective of our universe, it will look like a little particle. So different configuration of the strings wrapping around this extra dimension translates to different properties of particles that we can see. The extra dimensions can have amazing consequences. One of the predictions we are now making recently is that our universe, the 3-dimensional space, could be viewed as a sheet in one of these extra dimensions, which is bigger than the rest. Namely, you can think about our universe as a sheet with 1 extra dimension out of those extra 6 dimensions, which is of the order of 1 micron. Micron is about 1,000th of a millimeter, and even though it's small, it's not that small. It's bigger than atomic scale. So we think one of the extra dimensions may be that big compared to what these tiny other dimensions could have been. And if that's the case, it will change the force between particles, which is supposed to go like 1 over distance squared, according to Newton's formula, to 1 over distance cubed. In other words, at shorter distances, the force gets stronger than Newton expects. Which distance? Well, this distance has to be about a micron. So if the distance between 2 of the masses is less than a micron, the force should gradually change from 1 over distance squared to 1 over distance cubed. So there are experiments going on right now to try to measure these effects. The highly mathematical aspects of string theory is typical of many attempts to connect physics with reality. Can we illustrate this connection between physics and mathematics with simpler ideas? That is my aim here today. We're going to have mathematical puzzles in the form of simple questions that I'm going to address to you, not as simple as the first puzzle for which you saw the answer, but a little harder, but nevertheless not formidable, so that the answers are hopefully within reach. And I'm going to ask you to raise your hand when we have a guess about what the answer might be. This is motivated by a course I taught. I have been teaching actually at Harvard called Physics, Math, and Puzzles, which I have been teaching since 2012, which basically was the idea behind this lecture that I'm giving, and it's by now a book called Puzzles to Unravel the Universe, which is this book. So we have classes of about 12 to 15 students, and giving them puzzles, and some of the students bring puzzles to the class, and some of the puzzles we're sharing today come from students who gave these puzzles. So I will start with the first topic. So the basic idea is that I will start with a topic, we raise a puzzle, and then see how it goes. Symmetry and conservation law. This is one of the most important principles of physics. Physicists love symmetries. Symmetries, like a triangle which has two equal sides has a symmetry of a reflection from the middle. Okay, that's a symmetry. You might say, okay, that's fine, that's pretty, but what's it good for? So here we're going to give some example of how this kind of thing can be useful. So imagine having two containers, one filled with green paint and one filled with white paint. Same amount of volume in white and green. We're going to take a glass and pour it from one to the other, and at the end, ask you, what do you think about the distribution of mixture? So let's watch. You take this cup, fill it with the green paint, we stir it, it's important. And then take the same amount from the mixture and put it back into the green paint. We can stir it. Good. Now we put it down. Thank you. Okay. Now we ask a question. What is the question? The question is, which container has the higher mixture of the other color? Does the white container have more green in it, or the green has more white in it? Or are they equal? So there are three options. I'm going to ask you one by one. How many of you think that the white container has more green in it? Raise your hand. Okay. How many of you think that the green has more white in it? Raise your hand. Okay. How many of you think it's equal? Raise your hand. Okay, very good. Thank you. So majority of you went with the first option, and then the second most option seemed to be the third option. So I will first support why majority may have chosen the first option. The reasoning may have been, I don't know if it's exactly what those who voted for it thought, well, the white one is pure white, and you take pure green and put it into the white. So you put pure green to the white. Now, when you took the same amount from the mixture back to the green, some of that green went back. So therefore, the white has more green, obviously. That might be one reasoning. Actually, that's not the correct reasoning, even though it sounds very intuitively correct. And I want to use symmetries to explain why. The symmetry that we love explains why that's not the correct answer. And in fact, the third one is the correct answer. They are equal. Why are they equal? Well, you start by having equal volumes of green and white paint. When you switch back and forth, at the end, the volumes are totally the same as the beginning, correct? Because whatever the volume went back here. There's a conservation of green and white. so it doesn't disappear. So whatever is missing from the green one must be in the white, and whatever is missing from the white is in the green. But they started with equal volume, and they ended in equal volume. So therefore, the volumes that have been switched must be equal, just by symmetry. In other words, if you think about unmixing them, if you could do it, and then switch them, they must have replaced each other. Just symmetry explains that. You don't have to do any thinking. Now, if you don't believe it, do the calculation. Much harder. You'll find they're actually equal. So this is a kind of a surprise that, this simple reasoning gives the correct answer, and the other one, which is intuitive, is wrong. So symmetries are powerful. Now, let me give you another example of power of symmetries. Aristotle, this great philosopher, thought heavier objects fall faster. Everybody knows that a big stone and a pebble, which one falls faster? Of course, the natural instinct says the heavier object falls faster. Galileo said, no, all objects fall at the same rate. Okay. They said, Aristotle has said differently. How could you say such a thing? He said, do the experiment. We'll do the experiment. They said, no, experiment. This is, you have to give a reason why it's not. It's obvious that the heavier object falls faster. So he had to convince his colleagues why it had to be the case. This was a period where the science was less experimental viewed and more like theoretical, philosophical. And so for him, he had to come up with an intuitive argument to make it clear why objects fall at the same rate. Now, just to be clear, I know that the feather will take a while to fall down. I'm talking about objects in the absence of resistance by air. Which one falls fast? So if you ignore the feather one because of the air, somehow imagine that you're in a vacuum where nothing can cause resistance. And indeed, it's true that if it's no resistance, all objects fall at the same rate. But he had to convince people. So he said, how do I do this? He used symmetries. Galileo used symmetries to convince people the objects fall at the same rate. Symmetries? What does it have to do with falling of objects? This is how he did it. He said, suppose you have 3 bricks. Put them at the same height, and then release them at the same time. Which one will fall faster? Well, these are the same size bricks from the same height, all being released at rest. Which one will fall faster? Of course, by symmetry, all fall together. You see? That's obvious. You didn't need to do experiments. Symmetry tells you that had to be the case. Now, Galileo reasoned, suppose you take these objects and move one of them closer to the other and then drop it. What happens? The same, of course. As long as they're the same height, it doesn't matter. Is that obvious? Yes, because symmetry, there's a translation symmetry horizontally, which doesn't affect your problem. And then people said, okay, so what? What does it have to do with falling faster or slower? He said, well, does it matter whether I bring these bricks together closer and farther? They said, no, of course it doesn't. Well, said, okay, if it doesn't matter, I'm going to bring 2 of them closer and let them touch, like this one. And then let them drop. Does it matter? No, of course it doesn't matter. They fall at the same time. But then he said, that was twice bigger than that one. He tricked them. So basically, the symmetries allows you to make it intuitive. And that is the way physicists like to understand things. Like, it makes it obvious. Of course it's obvious when you see it this way. Now, I told you about symmetries. Now, why would I want to break them? Well, it turns out symmetries are very interesting, but spontaneous breaking of them is even more interesting. What does breaking of a symmetry spontaneously mean? I will explain with a puzzle. We have 4 cities, A, B, C, D, on the corners of a square. We have been instructed to build a highway system connecting all 4 cities. We have limited budget, so we have to make this highway system most efficiently with minimal total length for the highway. Is the question clear? So you're going to have to be helping me with designing these highway system. Ready for the questions? How many of you think this is the answer? Raise your hand. Oh, okay. How many of you think this is the answer? Raise your hand. Uh-huh. How many of you think this is the answer? Raise your hand. Okay, I see a few hands. How many of you think this is the answer? Raise your hand. Well, how many of you think this is the answer? Raise your hand. How many of you think none of these is the answer? Raise your hand. Okay, no, it was this one. It's not always the last one. Now, what does this mean? Well, look at it. This is a strange answer. It breaks the symmetry. You see, I'm saying that you have to connect the cities A and C together, make a 120-degree angle, go to the right, and split the other way for the other two cities. How could this be the answer? In other words, it is easier to get from city A to city C than from city A to city B. It's farther away to get from A to B. I broke the symmetry. The symmetries of the square is partly broken. Is that clear? That's strange. We started with a symmetric situation, but minimal cost of the highway forced a solution which broke the symmetry. This is what physicists call spontaneous symmetry breaking. You start with a symmetric situation, but the solution is not symmetric. And this is actually very important in modern physics. It underlies a lot of amazing things. But before I get to those, I want to say that this is not a modern concept. Greek philosophers already knew this. And so let me explain how they knew this. They had already discovered that the Earth is round, very smart people. And they thought it's at the center of the universe. And it's not moving. So it doesn't look like it's moving. And they have figured out it's a sphere. But then they would be looking like a moon seemed to be moving, the sun seemed to be moving, and all that. And somebody asked, by the way, why aren't we moving? So they had to come up with an answer. Why aren't we moving, but everything else is moving around? They thought it's a hard question. And then one of them said, aha, I have the answer. Symmetry. They said that we are at the center of the universe. And if we were to move, we have to pick a direction. Any direction we choose breaks the symmetry. So that's why we are not moving. That was the answer. In other words, we are at the universe at the center, and if we were to move in some direction, we break the symmetry. We are going in some particular direction. Symmetry is gone. That's forbidden. So therefore, that's not why it's happening. Break symmetry, forbidden. Okay. Aristotle said, no, not a good argument. He refuted this argument. He was very smart. He didn't agree with this argument. How did he refute it? He said, well, suppose you're in the middle of a circle, and all around you, there's loaves of bread on a circle around you, equally distanced. And you're right at the center, right? What's going to happen next? Are you going to stand there forever? Because if you go in any direction, you're going to break the symmetry. So he said, of course you break the symmetry. You go and get the food. So he argued that this, in other words, breaking the symmetry might be the preferred situation. Just like what happened in that square problem I told you about. You broke the symmetry to get the minimal area, minimal length of the highway. And here, Aristotle noticed the same fact. I don't think he thought about the suit man, but anyhow, the idea was what he had in mind. Very brilliant idea. In fact, you all have broken the symmetries on your bodies, and you probably may not recognize it. You see, we live on Earth, and on the average, all around us is symmetric if you rotate 360 degrees, on the average. But our bodies do not have that symmetry. In other words, our eyes are in the front, not all around us. Why not? What happened? Evolution did not understand that we are in a symmetric situation. We should have had all over us the eyes. What happened? Well, the reason is simple. We had to go for the food. Because we move towards the food. It's more important to know where we are heading to get the food. That's why we have eyes in the front. You might say, that's funny. No, I'll give you more evidence. Like trees, they don't move. They don't care which direction, so therefore they're typically more roundish. That's consistent with that fact. So our bodies reflect breaking symmetries. So we have the evolution has decided breaking the symmetry is better for us, and eyes go in the front. And physics has taught us that this is an important principle, repeats again and again and again. For example, we have learned the reason we have mass, like me, you, etc., particles have mass because there's a broken symmetry. There's a symmetry in the fundamental physics that if it weren't broken, everything would be massless, like light. We would have been zooming around with the speed of light if the symmetry was not broken. That's what's called the Higgs particle, is the origin of it, which was discovered in Large Hadron Collider. So that's an example of a powerful idea. Symmetry had to be broken. Why there is matter more than antimatter? There's this other thing called antimatter, which kind of, if it gets to matter, they collide and all energy comes out. If there were equal amount of them, they would cancel completely and nothing is left. But somehow, even at the beginning of the universe, they were almost equal in number. Somehow, when we are living now, there's more matter than antimatter. So there's a symmetry is broken. Magnets, they're pointing in some direction, breaks the symmetry. Superconductors, no resistance. How's that coming? How's that possible? These are all facets of breaking of symmetry spontaneously. Now, I want to show you that abstract math could be very powerful, but it doesn't have to be too complicated. Even simple math could be amazing. So I'm going to go through an exercise with you. Earth and the equator. So imagine this, our blue planet. This is maybe too blue, but anyhow, imagine this is the Earth. And imagine that white circle there is the equator. It looks like a belt there. In fact, think it's a belt. Think about this white thing in the equator as the belt, and open it up. So that's the equator right in front of you. And then add 1 meter to it. You see at the very end there, we just added 1 meter to that equator. And now we're going to wrap it around the Earth. It's not going to be quite snug, right? Just a little bit maybe up, right? Now, you're going to help me answer the question, how much is it lifted above the equator? Is the question clear? Okay, let me call that x, the unknown x. How many of you think that x is, let's say, bigger than a meter? Raise your hand. See if I can see how many of you are raising your hand. Okay. How many of you think it's bigger than a centimeter? Raise your hand. Okay. How many of you think it's less than 1 millimeter? Raise your hand. Okay. Okay. The answer is, let's see what's the answer. Simple mathematics will give us the answer. So let's figure out what's happening. The radius of the Earth is r, and the amount we have added is x. So the original circumference of the belt, the length of the belt, is 2 pi times the r. You may have seen this in elementary school, maybe. 2 pi times r. Okay. Now you add 1 to it. That's the 1 meter I added, right? And that's going to be the new circumference, which is 2 pi times the radius plus x, because the radius now is bigger by that x. Is that clear? Now, you may have seen the operation of multiplying out. If you multiply 2 pi times r plus x, is 2 pi times r plus 2 pi times x. That's like simple kind of algebra. And 2 pi r on both sides you can get rid of, and you get 2 pi times x is 1, and x, therefore, is 1 over 2 pi, which is pi being around 3. This is like 1/6, roughly. So it's about 1/6 of a meter. It's about 16 centimeters. This is quite a big number from, at least from what I would have guessed if I did not do the calculation, because the equator is huge, and you're adding this just 1 meter. It could rise 16 centimeters everywhere around the Earth. Surprising, but this is showing a simple math. Nothing fancy, just 2 pi r thing is giving you such an amazing answer. Now, sometimes you may need a little more fancy math, but this is showing you that even simple math could be interesting. So let me ask you a different question here. You see, I ask you what is the x, but I had put the belt equally distanced from the equator. But suppose you pull it on one side. If you pull the belt from one side, it will be snug on part of the globe, but some other part is going to be rising higher. Is that clear? So then x is going to become bigger. Is that clear? OK. Now again, ready for the question? If I did that to push the x bigger, how many of you think it's going to be raising up to a meter? Raise your hand. Meter? OK. How many think can rise up to 10 meters? Raise your hand. 100 meters? Raise your hand. OK, finally. Oh, somebody were raising? OK, nobody's raising. 121 meters. It is 121 meters. Isn't this shocking? Now, this one needs a little bit more abstract math. It needs a little calculus, so I'm not going to do it in front of you. But it is doing that math gives you this surprising answer. You just added 1 meter to the length of the belt, and suddenly it rises 121 meters above the Earth. Surprise, surprise. Continuity is an important concept in mathematics. And it tells you something about physical laws. It puts some restrictions on what can happen. Here we're going to go back to the Earth and ask about the power of that continuity for the Earth. Suppose I ask you the following question. Consider the equator and measure the temperature on the equator at any given time. So fix the time, let's say like, 3 p.m., and measure the temperature across the equator. Well, the temperature varies. It's not one number. As you go around the equator, the temperature varies depending on where you are. Some places may be hotter, some places may be colder. Could it be that 2 points on the equator, which are exactly opposite relative to the center of the Earth, exactly opposite to one another, have exactly the same temperature? Could be, right? It could be. But does it have to be like that? So, again, if you can roll up the lights, how many of you think that at any moment there are always at least 2 points opposite on the equator which have the same exact temperature? Raise your hand. How many of you think it depends on the weather? Raise your hand. OK. The answer is it does not depend on the weather. So you see, you say, why? How could it not depend on the weather? The idea that temperature varies from one place to another continuously, by that, what does continuous mean? Gradually. If the temperature is varying gradually, it cannot jump suddenly. It's just, if it's hot here, it cannot suddenly jump here. It goes gradually higher, lower, higher, etc. But gradual. Just that concept tells you that it has to be the case that at any given moment, 2 points across from the center of the Earth have the same temperature. How do we show this? Well, consider 2 points. The temperatures, let me call it T at each point. And consider if they are the same, you're done, of course. But suppose they are not the same. Consider the difference between them. The temperature on one side minus the temperature on the opposite side. Let me call this new difference, the difference between temperature, let me call it this function f. If f is anywhere 0, we are done, correct? Because when f is 0 means the temperatures are equal. So suppose it's not 0. Suppose we move these points as we go from one side to the other. As you go from one side to the other, what happens to f? F was the difference from one to the other, but as you go around the other, when you go exactly the other side, it's minus itself because you switch the two. So in other words, if you go the other side, f becomes minus itself. Because if this is higher than this by some amount, this one is lower than this by that amount. So therefore, the sign flips. Is that clear? So as you go from one side to the other, f goes from negative to positive or positive to negative. But this is gradual. If something goes from negative to positive or positive to negative, at some point, it crosses 0. That's the point where that difference is 0. Therefore, there's a point that have the same temperature. Is that clear? So this concept of continuity gives you things that you didn't think can be explained, but without knowing the physics or the weather. This tells you, no, you can. So math can give you some insights into what has to be possible. This is an example. In fact, it is more true. At any given moment, if you measure the temperature and pressure, there are 2 points on the globe opposite to each other which have exactly the same temperature and pressure. Remarkable. It's always possible. It's like if you open the news and said, today it was observed that at 3 p.m., this point and that point had exactly the same temperature and pressure, you say, wow, that's cool, isn't it? No, it's not cool. It's always the case. At any moment, that's true for some 2 points. The points might vary where they are, but there are always at least 2 points with this property. Simple continuity argument. I won't explain it, but similar to the argument I just sketched. Now, another concept, now I'm going to get to more abstract concept, gravitational lensing. Now, gravitational lensing is this amazing phenomena which gives you another example of continuity. So what is gravitational lensing? Einstein's theory of relativity predicts that when the light passes around massive objects, it bends the light. Okay, so suppose you have a faraway galaxy over there, up there, and we are here, down here at the Earth, watching the galaxy. So you look that way and you see the image of the galaxy, the light is coming. But then there's another path that light can take if there's something in the middle which can bend the light enough. So you see these 2 paths coming together. So if you look at the sky, you see, oh, there's a galaxy there. And then you say, oh, there's another galaxy there. Looks like 2 different galaxies, but they are the same. So this is called gravitational lensing. So you get fooled to think that there are 2 different objects, but they're actually the same object. It's just the light took a different path. So it's quite a fun. And people have, astronomers have seen many of these. For example, in this picture, like over there, you might say these are many different objects. Actually, the blue circles are the same quasar, and the orange ones are the same galaxies. It's remarkable, but it's hard to see it from this picture, but there is enough evidence that this is the case. In fact, there is a general phenomena. The number of gravitational images, if no image is blocked, of course you can block an image, so let's not block it, is always an odd number. It's either 1, 3, 5, 7, etc., but not 2, 4, 6, etc. It's always an odd number. And out of these number of images, just less than half of them are flipped. So for example, if you have 5 images, 3 of them are normal, but 2 of them are flipped. Always. Now, I'm sorry, you have to solve Einstein's theory to see this. No. It's easy math. Well, okay, I'm cheating a little bit. It's a little bit more fancy math, but you don't need to solve Einstein's equation. It is, again, follows from continuity, similar to this temperature thing I told you about. So the argument is a little fancier, so you may not quite follow what I'm going to say in the next slide, but bear with me so that at least I can kind of give you an indication of how these kind of arguments go from abstract math. The mathematicians defined the degree of a map. What is the degree of a map? It's the net number of pre-images of a given point. So a map takes one space and maps it to another space. And if you ask how many points got to that point and count them, each one is called a pre-image. You just count them. Now, if the image is inverted or not inverted, you count it with a plus sign and a minus sign. And the mathematicians prove that this is continuous function, so it doesn't jump. And therefore, once you measure it once, it's always the case that's going to be the same. Using this concept, you can show that the degree of the map is always 1. Because if there is nothing between you and the galaxy, the light comes out straight and you see one image. So if there is 3 of them, it better be that the net number is still 1. So 2 minus 1, so 2 images are upright and 1 is inverted. Or if it's 5, it should be 3 minus 2 to be 1. Or it's 7, it's 4 minus 3, it's again 1. So this continuity just gives you this answer without doing any calculation. And you can kind of see it with this picture. Like, you can see the galaxy, kind of the image getting once, with the geometry around the galaxy is distorted, but sometimes you see 3 images. Those are like those things that crosses that horizon. And if you go further, you can see 5. So these numbers jump by 2. And they come in pairs because you kind of go back and forth, up and down. And that's the inverted versus non-inverted. So one of the beautiful concepts in physics is duality. What is duality? Duality refers to the fact that sometimes 2 completely inequivalent physical theories are nevertheless the same. They look very different, but somehow magically they are the same. How do we illustrate this? Easy, by a drawing. This drawing by Escher. A beautiful drawing. You see, if I ask you, what is this a drawing of? And suppose I covered the whole drawing except the upper left corner. You would say, okay, it's some day and there are black birds flying on the sky to the left. And if I told you, if you just looked at the right part of it, you would have said, no, it's a night and there are white birds flying to the right. And if I showed the left and the right are down, you see, oh, no, these are black and white fields and so on. So you get completely different answers depending on where you're looking at it. But if you look at this whole drawing, it kind of gradually morphs from one side to the other. This is what duality means in the context of physics, that they could all be true. If I said, this is a picture of a day, you say, yeah, it is. Look at that side. And if I say, no, it's night, you say, yeah, look at the other side. They're both true. It's just have to know which part you're looking at. This is a kind of a concept of duality, and this is very important in modern physics. It has reshaped our understanding of many parts of physics, this kind of mode of thinking. So I'll give you a puzzle about dualities. It involves ants. I hope you like ants. We have a meter stick, 1 meter long, and then the ants are marching on this meter stick. But you can tell the ants whether they should go to the left or to the right. And you can place the ants yourself on the meter stick. Meter stick is 100 centimeters, and the ants go with the speed of 1 centimeter per second. Okay? Now, what do we want to do? We want to accomplish the following. We want the ants to last as long as possible on the meter stick, because if they go left and right, at some point they will go all the way to the end of the meter stick and fall off. Now, if the 2 ants come together and collide, guess what's going to happen? They go the other way. So they collide and bounce back and forth. So your task, if you accept it, is to put the ants on the meter stick and instruct them to go left or right in such a way that the last ant that survives lasts the longest possible time. So look at these ants. You see that red one bounces to the blue, and then this and that goes back and forth. And when they get to the boundary of at the end of the meter stick, it just falls off. So where do you put the ants, and which direction should they initially go so as to maximize the time the last ant falls off. Is the question clear? Okay, now if we put the lights back on, I'll ask the questions to you. How many of you think the best strategy is to put the ants in the middle and have them instructed to alternate going left, right, left, right, left, right? Raise your hand. Okay. How many of you think we should do the same, but put them at the left and the right boundaries, and the left one should all go to the left, to the right, and the right one should all go to the left? Raise your hand. How many of you think it doesn't matter where you put the ants? Raise your hands. Wow. Okay. How many, well, none of these I have to give you. None of these are correct so far. Now I'm giving you a hint, of course. How many of you think it's only relevant where you put one ant? Raise your hand. Very good, yeah. It's just one ant determines everything. What? One ant? Yeah, one ant. What do? You put the ant at the very left and say, go to the right, and that's it. You don't care where the other ants are. How could this be the answer? Dualities will tell you why. So I will illustrate the power of dualities just by proving that this is the correct answer. And you kind of see, it's obvious once I show you the picture. You see, I tried to confuse you a little bit by drawing colored ants. Are the ants colored, usually? No, this is a funny picture. The ants are usually black. And when they hit and collide and reverse directions, can you say if they reverse direction or went through each other? Nope. It's hard to distinguish. If the ants have the same black color, you don't even know if they're going through each other or colliding back and forth. Therefore, the answer is the same as if they just went through each other. If that is the case, you just put one at the end and say, go to the right, and you don't care what about everything else is going on. Is that clear? This is the power of duality. What did I do? I changed the problem to a dual problem. Instead of saying the ants go like this, I said they go like that, and the problems are the same. They're dual to each other. The problem did not change. Equivalent answer. But one of them is much easier to answer. Is that clear? So this is the power of dualities. So this is going to be my last puzzle because I'm running out of time. So I want to illustrate it by the important thing of what is the scientific methodology. We scientists are proud of our methodology. Let's do it together. What is our methodology? We first of all do experiments, which means look at examples. And then after the many examples, we formulate a principle, a law, a general idea based on those examples. And then come up with arguments, why it's correct or why it's not, try to explain the principle, and then continue doing experiments. That is scientific methodology, and we together are going to do an experiment right now. Are you ready? The light back up, please. We have a circle. We are going to do what? Well, we're going to put points on the boundary of the circle. 2 points. We're going to connect these 2 points together, and we are asking, how many regions do we get inside the circle? Well, in this case, it's kind of clear. We just get 2 regions. In other words, if we have 2 points on the boundary of the circle, we get 2 points, 2 regions. So 2 points, 2 regions, kind of obvious. Okay, how about 3 points? We connect them. How many regions do we get? 4 regions. 1, 2, 3, 4. Correct. Excellent. Now you're getting the pattern gradually. We want to give an answer to every number of points, right? Ready? The next one. 3 points, 4 regions. Okay, 4 points. How many regions? 8. Very good. Do you see these experiments? We are doing experiments. We are gathering data. This is our data. Is that clear? Okay, we have a chart. Experimental tables should be very clear. We are creating our own experimental charting of it. 4 points, 8 regions. Does anybody see a pattern? How many of you think the 5 points is going to be how many regions? 16. Let's see. 5 points. Yep, you're correct. Now, you might say, okay, so we have seen the experiment works, but why? Well, I give you a reasoning, see if it appeals to your taste. Well, each time you draw a line, a region is either on the left or on the right. So whatever region you have, you kind of double it. So each kind of line kind of doubles, left or right, so it's a factor of 2. Each additional point gives you a factor of 2, and that's what we are seeing. Is that clear? It's a reasoning. So what should we see if you have one more point? 30? Okay, let's just do it. So we get 6 points now, and then we count. I don't see 32. Can you count it again? There's a mistake here somewhere. I told them to be careful with the preparation of my talk. I don't know what they did here. No, actually, it is 31. There's no mistake. So much for our law. The law was a mistake. Our reasoning was false. Back to the drawing board. This is what happens in real life. We see experiments, we think we are very clever, we come up with a law, explain it, and then we do the next experiment, it doesn't work, like this. This one you can go home and check. I didn't cheat. You can do your own counting. It's painful. Now, of course, you can get less regions if you put judicious points. You can make points cross at the same point, the lines, I mean. I didn't do that. I take generic points. For generic points, you always get 31. If you put some special points, you can get less than 31, but never 32. Never 32. So therefore, that's the mistake. The law has to be corrected. And there is a formula. The number of regions is, there's some formula. You don't need to, that's not very relevant, but there is an exact formula. So there is an actual computation. Okay, so let me just stop here by saying that I hope I have conveyed the power of simple mathematics. We love simple ideas. Math is super powerful and super cool. And even the most advanced ideas in physics have simple mathematical underpinnings, like the puzzle we discussed today and manga type. Thank you. Thank you.